Welcome to lecture 29. Announcements as usual. No surprise about the homework that's due this week. A reminder that there's a Project 2 party tomorrow. In fact, there are two. There's one in person and one online. And I believe it's the, for the online one, it's the group office hours link. And we're back on, last time your lab was working on Project 2. This time we have a lab. Project 2 is due this Friday. I'm going to pause to give you a chance to ask Will some questions about details. I'll do my best to answer. Anybody? All right, so we have we're at a point where we're now going to do a couple of significant applications of everything that you have learned thus far. For the coming 2 weeks, we will talk about predicting one variable using information from another. And in the following 2 weeks, we'll talk about using the computer that's programmatically taking data and classifying it into group A or group B. And so today, what we're going to do is we're going to look at two numerical variables, and we're going to look at the relation between them. You have seen for a long time that any relation between them is called association. We'll look at a particular association, linear association. I think it's clear that that is the way to start. After all, if we can't handle linear association, we're unlikely to be able to deal with nonlinear. And then, so today we'll set up a numerical measure of that and look at how it should and should not be used, what it tells you and what it doesn't tell you. And then on Wednesday, we will use it to start predicting one numerical variable based on another. And there is a very famous method of statistics and data science called regression that is used for this. And I do believe that if you look at all data science methods used in industry, research, just across all disciplines, this is probably the most common. And then on Friday, we'll start talking about in what sense is this the best thing to do. But before that, let's do rapidly a review of where we ended up last time, because there were 3 discussion questions on the slides, which we didn't get to. So we'll just go quickly through them. So where we ended up was we were estimating a population proportion. By that, I mean there's a population and they all have some opinion, yes or no on something. You as the pollster have gone and taken a random sample, and in your sample, you see the sample proportion of people who say yes. And your question is, well, what's the proportion in the population? So you make a confidence interval that looks like this. You start with your sample proportion in the center, and you go some number of SDs on either side. And if you want 95% confidence, then you go, if your sample is large, you have the central limit theorem working for you. So you go 2 SDs on either side, which means 4 SDs in total. But you see, your estimate is here, it's the center. So how far off can you be? Well, the furthest off you can be is at one end or the other end, but it's the distance from the end to the center, because that's your estimate. And so that distance is called the margin of error, the distance from the center of an interval to the end. And you can see in the picture that it is 2 lots of the SDs. The margin of error assumes that you have calculated a 95% confidence interval. And so now we get into how do you calculate those widths. So the total width is 4 times the SD of the sample proportion. And last time we did a calculation. Last time it was on, what am I? a couple of days ago, you established that the SD of a sample average or proportion is the SD of the population divided by the root of the sample size. And so the margin of error, therefore, is two lots of those. And last time we saw, simply by calculating a lot of these SDs, that the SD of a 0-1 population is at most 0.5. So that allows us to get a conservative estimate of the total of the margin of error. And so the here is the headline of an article in the Scientific American, which asks a very reasonable question. How can a poll of only 1,004 Americans represent 260 million people with only a 3% margin of error? The idea here is that 260 million is a ton and 1,000 is relatively tiny compared to that. How is the margin of error so small? Clearly, the person who wrote the article was intending to imply that the margin of error should be quite a lot larger. But we can compute the margin of error. So we'll just do that. The margin of error is from the center to the end, so it's two lots of the standard deviation of the sample proportion. Okay, so I'm just going to write something and then you're going to tell me. So this is 0-1 population SD divided by what? Anybody? It was on the previous slide, square root of the sample size. So that was 1,004. Okay, and here the thing that we don't know is the SD of the population. All right, so you don't know it, so what can you do? Use 0.5 because that's the worst case, right? That's the biggest it can be. So this is giving you the biggest possible margin of error. And if I do that calculation, I have 3%. That's where that 3% is coming from. And so what you're seeing is that though 1,004 is small relative to the population, in absolute terms, it's quite large. Right? And that's the quantity that affects your accuracy, not so much the population size. You see, because the population size is so large that you might as well be drawing with replacement from that population, these 1,000 people. And so all that matters is the proportions in the population, not how many there are. And so let me just pause for a second and take questions on that calculation, and then we'll just go through the next one. Okay, so there are two questions. How do we get 0.5? We got it last time. We showed that the maximum SD, if you have a 0-1 population, is 0.5. It was the end of the last lecture. Why wasn't it 4 times SD? Because 4 times SD is the total width of the interval from left to right. We are instead looking at the margin of error, which is the distance from the center, because your estimate is in the center. So you're looking at the distance between the center and the end, and therefore it's half of this. That's the definition of margin of error a couple of slides ago. All right. So you will have noticed that in is the SD of a 0-1 population the same thing as the SD of the sample? No, it's the SD of the population. The SD of the sample is the SD of the zeros and ones in the sample. The SD of the population is the SD of the zeros and ones in the population. They may be close, but okay, there's a lot of questions about what's the 2 in the margin of error. 1, 2, that's the 2. Right, two SDs from the center to the end. Okay, we've been doing simulations now for many weeks, and we often repeat simulations 10,000 times. And thus far, we haven't really discussed it. It just seemed like a nice round number and we could do it. But now we were going to look at this 10,000 has a particular feature, which is interesting. So the question is, a researcher is estimating a population proportion based on a random sample of size 10,000. With chance at least 95%, the estimate will be correct to within what? So your estimate is some random quantity, and the center is going to be what you want it to be. The center is going to be you expect it to be the population proportion, but it's going to be off. So the distance between your sample proportion and your population proportion, that's measured by what? Your estimate in the sample and the actual thing in the population. What's the thing that measures that distance roughly? The SD, yes, not the sample SD, the SD of the sample proportion, right? Your sample proportion is maybe 61% or 62% or 58% or whatever. It's the variability of those numbers. And because of the central limit theorem, your sample proportion is roughly normal. So you have two measures, two of these measures is what you need. Here, it is, as a number of people have said before, the margin of error, right? That margin of error captures 95% of the estimates. And so can we calculate a margin of error? I think we can calculate a margin of error. We just did this. So in this case, we will have 2. We're still estimating a proportion. The worst case SD is 0.5. And so now 10,000 times 0.5. Before I run that, sample proportion SD and margin of error are the same. The margin of error is twice the sample proportion SD. 2 lots. Okay, so I'm going to run this thing. And I get 1%. Beautiful round number, 1%. So if I go back here, if you are estimating a population proportion and you are using a sample proportion to estimate that, with chance at least 95%, you're going to be correct to within 0.01. And what I'd like to do is show you what that means in an example. So I'm going to do the very first simulation that we did for you of a statistic, which is simulating the number of heads in 10,000 toss in 100 tosses. So I have a coin HT. I've defined num tosses to be 100. So this one simulated count tosses the coin 100 times and counts the number of heads. And then, no surprise, we are going to do it, and now 10,000 times. All right, this 10,000 is important because that's the number we're looking at. We're going to repeat the process 10,000 times. And that's going to chug for a tiny bit. And so we will have 10,000 repetitions of tossing a coin 100 times and counting the number of heads. And here is the distribution. Okay, now each of these bars is a proportion. So this bar right here, the area of these bars, this bar is the proportion of times we got 50 heads out of our 10,000 times. Now that's trying to approximate something. It's trying to approximate the exact probability of getting 50 heads in 100 tosses. Okay, now it's not going to be exact. Why is it not going to be exact? Why is it off? Why is it not the exact probability? There's chance involved in which way? The exact probability comes from using every single sample. We have used only 10,000 samples. Therefore, we are going to be off. Right? And now what we have said is we have some measure of how much we're going to be off. This proportion here that we are seeing is a sample proportion. The actual proportion is the true probability. And our calculation that we have just done that says if you repeat your experiment 10,000 times, you're going to be off by at most 1% in 95% of your simulations, that just tells you that you're off here. This area is off from the true area by about 1%. And you can be 95% confident of that. And that really, to have some sense of how well these histograms are approximating the actual underlying thing, you can use the result that we just 10K is the number of repetitions. It is the number of repetitions each time you are looking at the number of heads in 100 tosses. And the question is, we have used 10,000 samples to get this bar. We should have used all possible samples. So the 10,000 is our sample size out of all possible samples. Okay, quickly now. We've been doing 95%, 95%, 95%, 68% confidence. What's the difference? One SD above and below, right? One SD above and below. So the total width of the interval is how much? The total width of the interval is 2 SD. So the total width is 2 times the SD, 0, 1 population SD. And then just by algebra, the sample size is going to be obtained by dividing by the width. Let me take you back to a slide before I do this calculation. Hold on. Okay, so for 95% confidence intervals, the total width is 4 times your sample SD. For a 68% confidence interval, it's 2 times the sample SD. So if you want the sample size, then you just turn the sample, munge this equation, and you have square root of the sample size is the left-hand side divided by the total width. This is something that we have seen before. And so if I do this calculation, okay, yes, 0, 1 population SD, what do I do with that? Somebody asked, can I assume that that's 0.5? Am I assuming that it's 0.5? Is that what I'm doing? Am I assuming that they're all 0.5? What am I doing exactly? No, I'm assuming it's at most 0.5. It's a worst case scenario. It's an overestimate. Very good. Okay, so I get 40. Is that the sample size based on what you've seen? What is it? Square it. Thank you. It's the square root of the sample size. So for the sample size, I should square it. The 0.025 comes from the fact that the question asked for a width of 2.5%. Okay. Width, left end to right end. Here to the end, one end to the other end. Different from margin of error, which is half that. Okay, why don't we move on to the main business of today, which is, well, actually, of the next several weeks, which is prediction. And I'll remind you that we have discussed this before. We are going to make a prediction, and always we have incomplete information, right? You don't know exactly everything that you need to know for the prediction. And so one way of making predictions is you want to make a prediction for a particular person. You try to see if you have data for people just like that person. And of course, you know, there's a lot of fuzziness in what you mean by just like, but you've assuming that you have some description of what that means, you find others who are like that individual for whom you have the data, right? And so then you use those outcomes and to make the prediction for this person. Maybe you take like the center of those outcomes as their prediction. And I'll remind you that we've done this before. And so this is a data set that you have seen before, where you have data on the heights of adult children and the average height of their parents. And what we are trying to do is there's a new adult who has come along, and we have the average height of their parents, and we're going to try and make some kind of prediction for the child's height. And this is not done typically when the person is already an adult, because then you can just measure their height. But you can do it when the child is born, right? Because you already have the heights, the average height of the parents. So the first thing to do is to visualize. And we did visualize this, and we saw, okay, what is it about this scattered plot that is showing an association? What's association? You're all giving me a sign of an association, but what is association? Again, you're measuring slope, length. This is all math. What's association? The two factors are linked. Thank you. There is some relationship between the two variables. And you can see that if your graph has any kind of trend or pattern. And so now what we are seeing, is there any kind of trend or pattern? Well, yes. I mean, if the families where the parent average was higher also in general tend to have children who were taller. Okay, so that is what association is. And now there is a question of, can we use that association in any way to make the prediction? And what we'd like to do is say, well, for taller parents, we should predict a taller child. And so if the average parent height is 70, we're going to look at all parents roughly around here somewhere, and then find the average height of their child, of their children, and make that our prediction. This is something we've done before. And we took our definition of close to be 1/2 inch on either side, but you can define it in any way you want. And then we applied this function to every single row of our table, and we got a bunch of predicted heights. For every child, we got the predicted heights, and then we plotted the predicted heights, and we got this graph of averages, those gold points. And we said, oh, look, this is how we make a prediction. And indeed, this is exactly how we're going to make every prediction from now on, whether we're doing classification or prediction. You want to predict for a person, you find other individuals like that person, and you take some kind of center of their responses as your prediction. In this case, the responses happen to come out roughly on a straight line. And so what we're going to do now for the next little while is try to identify, can we identify what that straight line is? And the other thing we're going to do is look to see, right, if this is my prediction, then how far right here, then how far off am I going to be? Well, those are vertical distances, right? Because the actual heights are here on the vertical axis. And so we are going to look at the vertical deviations from this line. And it is apparent from the picture that if the scatter diagram were more tightly clustered about this line, then our error would be smaller. So all of these things are what we're going to try and quantify. So association is any link between two variables. If you have two numerical variables, there's trend, which can go positive or negative. Trend is an upwards or downwards slope to your scatter diagram. pattern is any kind of wave or any kind of difference from just a formless blob. The pattern that we observed was linear, right? The centers were following a straight line. It could also have been nonlinear. And so to discuss any of this, before we quantify, we are going to visualize. And so here's a new data set. Well, it's not so new anymore, actually. This is a few years ago. These were all of the hybrid vehicles and the year in which they had been originally released. The manufacturer's suggested retail price, this is dollars, acceleration, miles per gallon, and then what class of vehicle it is. And we are going to be looking at what is associated with the price. And so we just take a look at the price variables sorted. Then there was one particular Lexus that was very expensive compared to all the others. And then there was quite a lot of variation in the prices. So what we're going to do is, these are hybrid vehicles, and the whole point was that you get excellent mileage. So what we're going to do is we're going to look at the link between the mileage, which is miles per gallon, and the price. And we're going to visualize that. We are going to draw a scatter diagram. Notice something. What do you see? More mileage leads to better mileage leads to higher prices or lower prices? Better mileage is lower prices. Isn't that interesting? The whole point of hybrid cars is you get good mileage, but that is apparently not what we are paying for. So then what do you think people are paying for? Look at this. Luxury, yes. Anything else? Brand name. People with expensive, no, but they're all buying these cars though. Vroom, vroom, acceleration, that is a good thing to look at. If I look at acceleration, woohoo, the more acceleration, the higher the price. Now, okay. Can we say from this picture that that's why people are paying the money? Because no, we cannot. All we're saying is that the cars that have higher acceleration, please be very careful about your biases. Okay, we cannot just discuss people as groups in a biased way. So let's be extremely careful. These are all hybrid cars. What we can see here is that there is the hybrid cars that had greater acceleration were also the hybrid cars that had the higher prices. That's what we're saying here. We are not inferring any causation whatsoever. We don't have the data. Okay, because there could be confounding factors. We're just observing the results. Okay. What I'd like to do now is I would like to go a little bit further into the data and notice that the vehicles were of different classes. Now, so maybe people who are buying sedans are different from the people who are buying SUVs or large cars or anything like that. So what we're going to do is restrict to the SUVs. There are 39 of these. And I'm going to look at the same picture, acceleration versus a price, only for the SUVs. Now, this picture doesn't look that terribly different. It's linear, it's going up. It doesn't look that terribly different. Do you agree? Obviously, there's fewer points, but the general trend seems to be pretty similar. Okay, what we're going to do now is we're going to look at, for SUVs, the miles per gallon versus the price. That is interesting. It's still negative, but do you notice that this seems rather linear? Whereas if you to put all cars together, that's decidedly nonlinear. Agreed? Okay, so it is very, very important when you look at relations like this to think about the individuals on which these are being measured. Because if you restrict to different groups of individuals, you might have quite different pictures. So that is a useful thing to keep in mind. And we'll see that in a little more detail later. Okay, so one of the things that I'd like you to do is, when you look at a picture like this, it's kind of going up. When you look at a picture like this, it's coming down. Both of them look kind of linear. How much attention are you paying to the actual numbers that are on the two sides? Are those numbers affecting what? Little to none. You're just looking at the shape. Exactly. Well, so if those numbers don't matter, and that, it's actually important because acceleration is measured in some units, distance per time squared, and then the price is in dollars. So the units are quite different on both sides. But if those numbers don't matter, then can you tell me, based on what you know, in what units should we be measuring these things? If the actual standard units, that's what they're for. Standard units, just, how far away from average are we? How many SDs away? So remind me how to convert to standard units. So I have an array X. What do I do? Conversion to standard units goes how? Okay, X minus mean. Is this thing an array? Is this a number? What is it? Yes, I'll divide. But before that, is it an array or is it a number? It's an array. Thank you. All right. Is this resulting thing an array or a number? It's an array. We have taken the entire array and we have converted it, all the numbers, to standard units. This resulting array has what mean? When you have the entire list in standard units, the mean is 0. What's the SD? Very good. SD is 1. Terrific. And so now I'm going to draw the same picture. This is miles per gallon in standard units and price in standard units. And you can see this is the same picture as this one, just on a slightly different scale. Okay, the standard units are going to be important as we start devising a measure of how linear this is. Okay, and so also with the acceleration versus price. For some reason, okay, so this was the table for the SUVs. And we had said that this particular graph looks the same for as for when you have all of the vehicles, not just SUVs. And so we've just done that. Wait a minute. I've just drawn the same picture twice. I do not need the second one, never mind. This picture is in the original units and this picture is in the standard units. Is the same thing. We're converting them to standard units because we observe that saying this is a positive trend and saying that this is linear has nothing actually to do with the numbers on both sides. Right. And so we're just going to, it doesn't matter that once something is measured in dollars or something is measured in something else. So we're just going to measure everything on the same scale. So we have standard units here. Okay. So now we're going to try and quantify, and the correlation coefficient is a mouthful, but it's a number that measures the degree of linear association, a very particular kind of association, because nobody can say correlation coefficient without breaking their teeth. We call it R. Okay, so it's based on standard units for reasons that you've just seen. It is a number between -1 and +1, which we will not prove here. You take your subsequent class and you'll see it there. When it's +1, the association is perfectly linear. So you have a straight line, and the plus says the line is going to be sloping upwards. Similarly, for -1, the line is sloping downwards, perfect straight line. R equals 0 is very, very strong. No linear association, uncorrelated. Please note, though, the word uncorrelated there, what does it mean? It does not mean no association. It means no linear association. Okay, so let's take a look at, we defined a function for you. It's called R scatter. And I'm going to put in -1 as the argument, and I get a scatter diagram that's a perfect straight line sloping downwards. Okay, so this argument is the value of a correlation. Tell me something else that I could put in there that is a correlation. Okay, I'll put in 1. Is that what you expected? Yes, so somebody suggested 0.5. Okay, if I put in 0.5, is the scatter going to be sloping up or down? Up. Is it going to be fuzzy? Yes, that's what we get, 0.5. And notice that this is very, very close to what you saw in the heights data. So somebody else had asked for 0.35, more fuzzy or less fuzzy? More fuzzy. Right, -0.35, same thing, sloping downwards. So it's the magnitude of R. It gives you some sense of how fuzzy it is. The smaller the R is, the smaller the R is, the more fuzzy the picture. The higher the R is, the higher the picture. Somebody wanted 0.99. The data are generated at random using, we've generated football-shaped scatter diagrams based on the normal distribution. But it is just to give you a sense of what correlation is doing. And I think what you're seeing is measuring the degree of, if we run it again, you'll get a different plot with similar, very similar R. Yeah, exactly. So these are randomly generated points. I forget how many points I generated. But you can see that R is somehow measuring the degree of clustering about a straight line. Okay, so what we're going to do quickly is calculate it. And so I have just created a list of 1, 2, 3, 4, 5, 6 points. And I want to show you the scatter diagram. Okay, can somebody tell me, if I calculate this, the correlation here, am I going to get a number that's positive or negative? Which? Positive. Am I going to get +1? I'm not going to get +1. Clearly what I did was I took a perfect straight line and I broke it, right? So these 2 points are not, I'm not going to get +1. Okay, so the first thing we're going to do is just convert everything to standard units, because it's not so much what numbers are along here that matters. And so we are going to work in standard units. And if I draw the picture in standard units, you get exactly the same picture, right? It's just the numbers are different. Okay. So what I am going to do now is something that has a mathematical justification, but I am going, which we're not going to do. I somehow want to connect these two. And I'm going to connect by simply multiplying them. And why we're multiplying, let's see in a minute. But I'm just going to multiply the standard unit. So I got the minus 1.46, etc., times minus 0.64, etc., to get 0.94, and so on. And then I am going to take simply the average of these products. So I have this whole bunch of products. I'm going to take the average of the products. That is, by definition, the correlation. And I'll give you some intuition for these moves, the product in particular. So, but for now, I just want to go through the sequence. So you convert your lists to standard units. Then you multiply them. So you now have a list, an array of products, and then you take the average, and that's R. And this number measures how clustered the scatter is around a straight line, and can only ever be, if you do this calculation, it can only ever be between -1 and +1. And this is all sort of mathematical results, which in this class, we're going to ask you to take on faith. You take another class, you will see why these things are true. Okay, so what I'd like to do now is look at this the sign of this. The sign of this is positive, and you told me without doing any calculation that I'd get a number that is positive but not 1, and that's exactly what we got, right? We got 0.617. Okay. I just want to show you where the sign comes from in the calculation. What do negative standard units mean? If something's negative in standard units, what does that mean? It's below average. Okay. Now, positive association means that the numbers that are below average in one variable also tend to be those that are below average in the other. The numbers that are above average in one variable also tend to be those that are above average in the other. And you know that here is a number that is below average in X, and here's its corresponding Y value is below average. What the multiplication does is it gives us a positive number. The two minuses become a plus. So also here is a number that is positive, that is above average in X and above average in Y. Its product is then a positive number. Now, not all have the same sign. So here is a number that is above average in X, but below average in Y, and its product is negative, but by and large, the products are positive. All right, and that is a way of seeing why the product is a good move to make. It's a simple move to make. It happens to give us a quantity that has nice properties. And so we'll talk about those properties in just a moment. What I'd like to do is collect all of this into a function that is called correlation. It takes 3 arguments: the name of a table, the label of the X column, the label of the Y column. And it returns the correlation between those 2 columns, and we're assuming that those 2 are numerical columns, okay? So we have to first take this X column and convert it to standard units. Did we write a function to do that? We did. It was called standard units. What does that function take? We go back, it takes an array. So I need the array of numbers that is in this column. So how do I get that array? Okay, so somebody yes, so we take the table and we apply dot column to it. And do I put an X or do I put an X in quotes? Okay, so we've had both numbers. Quotes, no quotes. Okay, this is why I had the blank there. This argument X is the label of a column. It already will have quotes, right? So you just pull that argument down here. And for Y, you do the same thing. So, except you have Y instead of X. Okay, so please make a note somewhere. You are going to have to be able to define these functions, standard units and correlation, by yourself. Okay, so please make a note somewhere. What I'm going to do is I'm going to apply. My table was called T very boringly, and its columns were called X and Y very boringly. I'm just going to apply my function and see what I get. I get 0.6174. What did I got before? 0.6174, same thing. Excellent. Okay, so now we are going to look at our SUV picture. This is mileage and suggested retail price. And the correlation will be, you agree, is going to be negative, but it's not going to be -1. And our function gives us -0.666. Okay, that makes sense. So also acceleration and miles per gallon positive, but not 1. And we have 0.48. Okay, questions about the calculation. We'll talk about interpretation in the remaining few minutes and just continue to do that a little bit next time. There is a built-in function, but we are going to use our own because we are going to use it for regression and so on, which it'll help to have it in this particular form. Okay, one thing I'd like to do is look at this product, okay, and observe that the calculation is symmetric in X and Y. You convert both to standard units, you're doing the same thing. When you multiply the standard units, does it matter which one you called X and which one you called Y? No. So by calculation, the correlation between X and Y should be the same as the correlation between Y and X. And I just want to make sure that we actually believe that. So the correlation between X and Y is 0.61. And so there was my picture. Okay, if I switch X and Y, will the graph go down? How many people think the graph will go down? How many people think the graph will go up? Switching X and Y is a reflection. It's a reflection about what line? The X equals Y line. If I switch X and Y, so I just do the scatter YX instead of XY, I get exactly the same thing, except I have flipped it about the X equals Y line. Right, same picture. You can kind of see both there. Okay, same picture. Now look at the two pictures. Think about the degree of clustering about a straight line. Is it the same or different in the two pictures? It's the same. You should get the same answer. And indeed, if I run my correlation function T with Y first and then X, I get the same thing, right? So very important that you can now talk about the correlation between height and weight. You don't have to worry about whether you should say weight and height. You also don't have to worry whether you should say the correlation between height in inches and weight in pounds versus the correlation between height in centimeters and the weight in kilograms. Why? Because correlation depends only on standard units. So therefore, you can refer to the correlation between two variables. The order doesn't matter and the units of measurement don't matter. Is the correlation we're calculating the same as R? Indeed, this is R. So I just want to make a few points about interpretation. You already know we cannot conclude causality. I want to talk about nonlinearity. R measures linear association. Okay, I am making a table here with a bunch of numbers, and so X is going from -4 to 4, and Y is X squared. Okay, look at that. Do you see an association? Is there an association? Sure, there's an association. That's a beautiful pattern, right? In fact, Y is exactly a function of X. It's not linear. If I calculate the correlation, my table is called nonlinear. My variables are X and Y. I get 0. Make a note here. Correlation is measuring linear association. And what we're saying here is that there is no linear association. So when you want to say two variables are not related, please say they're not related. Please don't say they're not correlation. They're not correlating, right? They're not correlated only means they don't have a linear relation. What is the implication of converting nonlinear relationships to linear ones? Where did I do that? I don't believe I've done that. So maybe you're asking about something that is unconnected at the moment. So I took a nonlinear relation and I measured the degree of linearity. And the degree of linearity is 0. But these two variables are clearly related. You say, if you want to say that two variables are not related, you say they're not related. You don't say they're not correlated. Not related is stronger. Okay, I want you to see what happens with outliers. I'm going to draw you a scatter diagram. Okay, everybody, correlation, how much? 1. Okay, I'm going to put in 1 outlier. Let's just check that our correlation function gives us the right answer. Okay. Okay, so I've taken my line, right? And I've put in this thing is an outlier. It's not following my line. Okay. Clearly, it is going to affect the correlation because now my points are not all on a line. It's not going to be 1. What is it going to be? Let's work out the correlation. 0. That single 1 outlier took you from perfect correlation to 0 correlation. Okay, so watch out for outliers. If you have outliers, don't calculate correlation. Deal with the outliers. Think about why they're there. Think about whether you need them. And if you need them, then don't calculate correlation. So you're not going to get a sensible measure. Okay, I am actually just going to stop here and pick up again